Now let's take a look at the properties of candidate elimination. Now, candidate elimination is we can regard it as an upgrade to FindS because instead of returning just one simple maximally specific hypothesis, it's returning the entire set of valid hypotheses encountered so far that are consistent with the data set. Does it still suffer the same type of problems as FindS? For example, does it handle error or noise any better? In fact, it doesn't. Let's take a look at the case where we have the following training examples. Again, these are the same ones that we saw earlier in the trace of the candidate elimination algorithm. Let's say the second training example is incorrectly labeled as a noisy example and is labeled negative. What's going to happen then? Well, let's step through the candidate elimination algorithm to see what type of problems that has. Again, we're going to start with an S0 and a G0, where the G0 is going to say all drinks are all okay, that the target concept enjoys all the drinks. And this most specific one is basically saying that I reject all the drinks. I don't like any drinks at all. And then all of the version space, which lies between these two, will contain all of the possible conjunctive concepts that we can represent. Now, after seeing the first drink, which is a positive example, we have to make more general the most specific case, right? So this is just going to write this specific training example into that because we now know there's at least one drink that the person prefers, right? Kopi, si, croissant, bang, gao, and lim. Okay, so that's all good. Our G1 is going to be the same. Okay, but let's see what happens when we see the next example. Okay, here we've gotten to our negative example, and you can see that there's a difference in this one. And because it's a negative example, this basically is going to make more specific our general concept, right? We're going to have to move to G2, and our G2 is going to be the case that we will have our our version space made more specific. So in specific, we see that croissant is okay, but gadai is not. So we're going to put this as the border, and we're going to put don't cares for the rest. Okay, so that's what we did for the second one. All right, so this is going to run into problems where? Actually, it's going to run into problems here when we get to X4, right? Because X4, you can see there's a case where there's a drink that we want extra sugar or gadai, right? But our most specific, our general border here already says that I cannot prefer any drink that has any value except for croissant here. And so that's going to run into a conflict. And as soon as I get to here, both my specific and general hypothesis are going to converge to null, right? So there's basically no way that I can represent the concept that I'm seeking, right? And so you can see this specific and general sets are going to be reduced to null with sufficiently large data here. Actually, not very large, just three examples, right? So this one, and this one is enough to show that it wouldn't converge. And that's going to be the case even in the case where our target concept is actually not even in our hypothesis set, right? So our S and G is going to be reduced to null in the face of sufficiently large data there too. We might also think about the case where the candidate elimination algorithm can poll the target concept for specific drinks that the person might like or not. Okay, this is in contrast to when a data set is just presented to the learner to learn from. Okay, so this is called active learning because basically the algorithm is proposing instances to be classified. So let's take the case where we exposed our algorithm to the same target examples, the 4 training examples as we saw in the candidate elimination trace. And let's say they were correctly labeled and we were able to generate this version space that we ended up with last time, which has 6 hypotheses in it. So what type of instance should an active learner request in order to best discriminate among the remaining hypotheses? Well, just like the game of 20 questions, we might want to try to do that in such a way that exactly half of the hypothesis in the version space would satisfy the particular drink or instance and would not satisfy the rest. If we can do that, that's going to help us establish what types of traits are left, okay? So for example, in this case here, we are setting the remaining examples in such a way that only half of these 6 hypotheses would be able to classify it positively one way and negatively the other way, okay? So in this case, we're basically trying to cancel half of the hypotheses that are remaining in the version space with that particular example. So this is exactly like the idea of binary search, where we're trying to reduce the version space as quickly as possible. And this means that in the optimal case, where we can get such instances, we are going to require at most an upper bound of log 2 to shrink the target concept space down through our version space to find the actual target concept F. Okay, so all the time we are moving our specific boundary downwards towards the general boundary, and also the other way around. These are monotonic advances, and when they converge to a single hypothesis, then we know we've actually converged to the target concept that we're looking for. Now, even in this case where we've run the candidate elimination algorithm only on 4 examples, we've gotten a version space, but we haven't converged to the target concept yet because there's more than one hypothesis still left in the version space, right? There are 6. So can we use this partially learned concept in order to classify new instances? In fact, we can, right? So let's take a look at this case of this target example, which might be a test instance that we expose our partially learned concept to, right? So this particular instance has copy, si, kosong, peng, po, and dabao, right? And if you look at this particular instance, we can see that it actually checks off, that means it's satisfied by all of these particular ones because it has these 3 attributes set positively, right? So we can say that this case is definitely going to be classified as a positive example because every single one of these 6 hypotheses also returns us a positive value, okay? But we might want a more efficient way to test for this, right? Because if our version space is large, we'd have to go through all of the different ones that are in between the boundary of this, right? So one efficient way to do that is to notice that in the version space, if we take a look at a test instance that satisfies every one of the members of the most specific set, then it's going to be fine. It's going to be unanimously decided as a positive instance for all of the hypotheses in the version space, okay? So we can see that here, right? So in the case where the first most specific hypothesis space also says that it is a check mark, then everything below it must also say it's a check mark. That's what we're trying to say with proposition 3. And so let's take a look at this proof, all right? First, we're going to take the givens here. We're going to say that everything that satisfies all of the members of the set S, okay, here we only have 1, will also, this is what we want to prove, satisfy every H in our version space. So it will satisfy all of the remaining ones down here. That's what we're trying to say, okay? So by implication that when we satisfy here, everything below it will also be a check mark. So we're given this as our given, so that's fine, okay? Then what we're going to notice that because we have this binary operator to say that S is more specific than all of the H's inside of our version space by what we talked about earlier, our version space representation theorem, okay? then it's the case that if S gives this a positive example, meaning it satisfies it, okay, that means our hypothesis, any hypothesis in our version space, will also give it a positive rating, right? By the definition of what we said is more general or equal to, okay? And by this, we can conclude that all of the hypotheses in H, in our version space, will also return a positive value by looking at both of these steps, right, from here and here. Okay, so that satisfies it in one direction. We can also do this part here, which we're not going to do in this video, where every input instance that satisfies every one of these H's in our version space also satisfies this, right? We need this bijection. Okay, what about this test example, right? This one is a black tea without sugar, okay? Well, in this case, we can see that every one of the hypotheses doesn't accept it. So that's going to be the case that this particular trading example is going to be selected as a negative or -1, right? Okay, and this is also satisfied in the opposite direction, okay? So we can do the same types of proofs. We're going to say an input instance X that satisfies none of the hypotheses in the version space is going to be the case when it satisfies no members of the general set, okay? So it means that we don't have to test for all the ones up here. We can just do a more efficient test and just test for the case that none of the members in G, here we have 2 of them, accept this particular instance, right? So this is very easy to see. It's not a coffee drink, and it's not using evaporated milk. So both of these attributes are out. How about this third instance here? Well, let's go through and see what we get. This is coffee C, but it's not ice drink. It's actually hot, so it doesn't satisfy this. And it won't satisfy this one for the same reason, or this one. But it does satisfy the remainder. It is a coffee drink, and it does use evaporated milk. So here we can see our version space won't help us, right? Because we have 3 positive cases and 3 negative cases, so we don't have enough information to decide. So what about this final instance, test 4? Right, here we have a tea drink that uses evaporated milk, no sugar, iced, it's thick, and is for here. In this case, we're going to take a look, right? So it doesn't satisfy the case of a coffee drink. So this is no, this is no, this is no, this one is no. But it does satisfy the other 2, right? Because it is using evaporated milk as well as ice, okay? So here it looks like we're going to vote and just say, use the majority of vote and say, this looks like it's a negative instance, okay? But we can't be 100% sure, but because we have a version space, we can let all of the particular hypothesis vote, right? If we do this, this means we accept all of these particular hypotheses as equally or uniformly probable, and we're going to output negative with a 60% chance of confidence, right? Because we have basically 2 out of the 3 different hypotheses, or 4 out of the 6 hypotheses as voting negative.